a real pleasure to introduce Professor Ravin Bhatt from the Physics and Electrical Engineering departments at Princeton University. Ravin is one of the pioneers in the area of disordered semiconductor physics, disordered systems in general, quantum Hall effect, and so on. The long list of topics in which he's an absolute expert. He started his career after his PhD at Bell Labs in the 70s and rose very quickly to be the head of the physics division there before moving to Princeton University as a professor in the 90s. He's well known for many things in disordered materials, but perhaps the thing I like the best, because I've worked on it myself, is the Bhatt-Lee phase of random antiferromagnets in, for example, phosphorus doped silicon. And as a result of all these research experiences that he's had, we are in a unique position to hear about disordered systems from one of the pioneers in the field. And he's going to give us a series of 8 lectures, 4 of them in the Kulaba campus and the next 4 in the ICTS campus in Bangalore. The first 4 will be on Mondays and Wednesdays at 2:30, and the next 4 will be on Tuesdays and Thursdays, I think. And they are all going to be hybrid, so you can attend on Zoom as well. So without further ado, Ravin.
Thanks, Kedar. Can everyone hear me? Kedar, can you just respond to that?
Yeah, absolutely. Everything's good.
All right. That's great. Unfortunately, this somehow the other, the pointer doesn't seem to. Where are there? That should be there. Laser pointers. It's not working. Anyway, doesn't matter. You'll have to do with the little arrow that shows up in the in this screen. So the title of my set of lectures.
There is a point. There's a wooden pointer.
Yeah, I can use that.
Yeah.
All right. So the title of my lectures is From Single Particle Localization to Many Body Localization, and my plan is to start really from the ground up. So the idea is that I don't want to fill these lectures up with lots of algebra and integrals and mathematics. I want to convey some physics information to you. And hopefully I'll get through doing that by going slowly and starting right from the beginning. Okay, so the plan of the first lecture is just prehistory of the metal insulator transition. How did that come about to begin with? And that's what we're going to talk about all of today. I will talk about some early models and some early results, and then I'll bring you up to the late 70s. In 79, there was a very famous paper by Abrahams, Anderson, Lichatello, and Ramakrishnan called the Scaling Theory by the Gang of Four, and that's what we will talk about in the second lecture, and its ramifications. Now, this particular model applies to the problem of electrons in a solid which is disordered, but there's no interaction between electrons, which is of course not true. As we all know that in the metal, electrons interact with a Coulomb interaction that is screened by the other electrons, whereas in the insulator, it's unscreened. I mean, it's screened by the dielectric that's there, but it still has 1/r dependence. So we will talk about what electron-electron interactions do to this problem, and then confront experiment. See whether the experiments agree with having interactions or not having interactions and things like that. Then I'll move on to discuss in general the dielectric behavior across the metal insulator transition. In particular, we're going to concentrate on the frequency dependence of the dielectric constant, how it varies when you are in the insulating phase, how it varies when you're in the near metallic phase, and then finally in the metal. Then I will talk about a few things in this way of thinking about the metal insulator transition. The insulating phase is actually the strong coupling phase. So one would think that one really doesn't know how to handle that problem. But it turns out that there are at least two different aspects of the insulating phase that are quite under control. One is what's known as variable range hopping conduction that was solved by Halperin and Langer in a rigorous paper in the 70s. And then the second one, as Kedar mentioned, is the calculation that Patrick Lee and I did on the magnetic behavior of these systems at low temperatures. And both of them are, in a sense, controlled calculations. They are not just ad hoc. Okay, then I will move on to seeing how the magnetic behavior changes as you go from the insulating phase to the metallic phase. And that sort of will complete the course on just ordinary systems with where there's disorder, electron-electron interactions, but no magnetic field. And then I'll take a big jump to the high magnetic field regime for two-dimensional systems, the so-called quantum Hall regime, and talk about localization in this problem, and point out how topology affects the localization properties in this regime compared to when there's no magnetic field added. And finally, in the last lecture, I'll talk about many-body localization. Again, I will concentrate mostly on the quantum Hall regime as an example. We have some data on that showing how topology affects many-body localization. I think that's an important aspect that not other, there have been other studies in spin systems, but they don't really address that issue as well. So that's what I will concentrate on. So let's go now to the first lecture. And what am I going to cover? First, I'm going to just do solid state 101 or 001, whatever you want to call it, just good old band theory for a simple one-dimensional case, because that tells the point. But if you generalize higher dimensions. So we talk about periodic lattices and asking whether systems are metallic or systems are insulating. The next thing I'm going to talk about is the fact that band theory doesn't always give you the right answer. And that was something that was noted by Neville Mott already in the 1940s. He had a paper in 1949 where he shows that you can actually have an insulator because of interaction effects. Mott's original idea was a little bit misguided, it turns out. We'll talk about that, but nevertheless, it was extremely important in this whole business of understanding that band theory is not the solution of everything. A completely different model was done about a decade later by Phil Anderson, where he pointed out that if you had disorder in the system was not perfectly periodic, then you could get insulating behavior out of that kind of a model as well. So here is the Anderson model, which has no electron-electron interaction whatsoever, just purely a disordered potential, and then talks about how you get an insulating phase. And most of the data that I will show will be for doped semiconductors, because that was actually the particular material that motivated this whole question in the first place. But of course, there's data in other things. You have dirty metallic films, you have all kinds of other platforms, and I will talk a little bit about them, but because the most complete experimental data exists for doped semiconductors in the three-dimensional case. And even in two dimensions, when we talk about quantum Hall effect, the best data is all in semiconductor structures. So that's just what nature has given us. Semiconductors are the purest forms of solids we can have. If we could only make high-temperature superconductors like semiconductors, we know a lot more about what's going on there. But I will go back, over half a century to ask the question, what is the right model to use when one is going to talk about in metal to insulator transition in these doped semiconductors. And I'll give full detail about how semiconductors are doped and what kind of models we use to describe it. So that's basically today's lecture. So, band theory. I'm going to take a one-dimensional problem. I'll assume that there is some kind of ring of atoms where I've joined them at the end, so it's got periodic boundary conditions. I don't have to worry about edges, because edges only give you some surface effects, which should, in the thermodynamic limit, not be important. So if you just take a simple band structure of this, if these were free electrons, of course, one could write down the energy versus momentum relationship as b squared over 2m or h bar squared k squared over 2m, so that's that parabola right here. Now, if it turns out that you have a periodic potential due to the lattice, because of the ions, then quite generically, what you find is that this parabola breaks up into bands which can be all mapped on in k space from minus pi over a to plus pi over a. There's what's known as the extended zone scheme, where you have a band here, a second one there, etc., but you can always mathematically map it all back into what's called the first Brima zone. And what you find here is that in this case, is that you get bands which have gaps at the Brima zone edges. The gaps depend on the nature of the lattice potential, but generically they are there, and what you find is that you can actually do electron counting very easily as to find out whether for a given set of atoms, how many bands are filled. Okay, that's a very simple calculation. And actually, I'll just do that. It turns out that each band can accommodate 2 electrons per unit cell, one with spin up and one with spin down, in this non-interacting model. Because electrons are not interacting, it's a single particle problem. We have put electron in a periodic potential. What you see very clearly is that you need to have this, because the nth atom is going back to meeting the first one. There's a factor e to the ikNa, which must be equal to 1, because we want the wave function to be become itself when we go through the whole lattice, and automatically that tells you that this quantity k must be 2 pi times an integer divided by Na. And so the allowed k's for a given finite number of atoms, they are spaced by this amount, 2 pi over Na. Okay, that's just coming from just saying that this is equal to something times 2 pi. So p times 2 pi. Okay, so therefore, that immediately tells you that the total number of states in the Brima zone is exactly equal to the number of atoms. Or more generally, it would be the number of unit cells if you have a 2-dimensional system, or even a 1-dimensional system with a complicated unit cell. And since fermions for Pauli exclusion principles have to occupy different states, it means that if there are 2n electrons in a band, where n is the number of atoms, then you can have, in a given band, 2 electrons per unit cell, or 2n electrons totally, one with spin up, one with spin down. So if you use this mnemonic, what you find is that if the bands are not overlapping in energy, which in simple models, they don't overlap generally. You have to hook up with some kind of more complicated potential, and then you will, of course, get overlapping bands. But let me take the simple case where the bands don't overlap with each other. And in that case, it tells you if you have your atom has only 1 electron in this 1 atom per unit cell example, then the first band is half full. because it can accommodate 2n electrons and you have only n. On the other hand, so you have a metal. Why? Because your Fermi energy then is there are continuous states with arbitrarily small energies near the Fermi level. And so you can have excitations and you can have conduction. You apply an electric field, you get some response to the system. On the other hand, if you have 2 electrons per atom, then of course you fill up the first band, and the second band would be empty, and you need to actually give the filled electrons a finite amount of energy to go to the second band. So there will be no DC transfer. You put a small electric field, you get nothing out of it. So this simple example says that if you want to get an insulator, you need an even number of electrons per unit cell. If you have odd number, you'll always get a metal. If the bands overlap in energy, then you may get a metal if you have even number of electrons also. But the requirement for an insulator is very clear. It says that you've got to have even number of electrons per unit cell. And that's a result of band theory that you cannot change. And as I mentioned, this result is valid in higher dimensions as well. I've done a one-dimensional example, but that's just for convenience to go on to the next topic. So now I come to 1949. Band theory was in a lot of, there was a lot of excitement about band theory. Slater and many other people were calculating bands of various kinds. There were people, even like Wigner, who were involved in some of those early calculations. But what Mott said was something that he found sort of from experimental data. What he found was that if you have a semiconductor and you dope it with some amount of impurities, these impurities typically, as I'll show you later, create hydrogenic states. Basically, they are fat hydrogen atoms that are anywhere from 10 angstroms to 500 angstroms in size. But their basic physics is that of hydrogen atom. So it's 1 electron per hydrogen atom. And what was found experimentally was when you dope it very lightly, if you don't put too many of these dopants, the semiconductor remains semiconductor. It did not become metallic. Whereas band theory would say immediately that you have 1 electron per site, and therefore it should become metallic because it's only a half-filled band. So Mott's idea was the following. Suppose I had an isolated hydrogen nucleus plus an electron. So there's 1 dopant atom in the system. It would bind, the electron would bind to the nucleus in a 1s orbital. And so he said that then it won't go anywhere. Okay? On the other hand, if I imagine that I had lots and lots of these impurities, so there were lots and lots of electrons, I could imagine that these electrons could be described by band theory and they would be some kind of a band that would be half full. So he realized that the reason why the electrons are binding to the potential was because it's a 1/r potential. And you know that a Coulomb potential has an infinite number of bound states. So you can't escape that. On the other hand, if you have a high density of electrons, then you can show that the Coulomb potential will get screened. And most people, the simplest approximation for that is the Yukawa form, or the screen Coulomb potential. That is, it's just the Coulomb potential E squared over R with a negative sign between an electron and an ion, except that this has this extra factor, exponential factor, where lambda is called the Thomas Fermi screening length, and there's a formula for it. If you go to Ashcroft and Mermin or any solid state physics textbook, you'll find that there's a very simple formula connecting the density of centers to the screening length. So what you see is that the screening length goes inversely as a very small power of the density, actually, 10 to the 1/6. But as the density gets large, the screening length becomes shorter and shorter, and therefore this exponential factor dominates the Coulomb potential, and this potential stops binding in 3 dimensions. So that would say that a picture of essentially free electrons with a mild perturbation caused by the ions is a pretty good description in that case. So for high densities, he said that you would be happy with the metallic picture, but at low densities, clearly something else is happening.
In this picture, you can also consider the fact that in your, let's say, 1D model that you started with,
right,
you have one potential which is very different. Because
right,
you look
right,
at the periodicity.
right.
That would also give you a bound state.
Exactly, you do.
You don't need the 1 by R explicitly.
No, well, certainly not in 1D. So I'm talking about now, I just use the 1D as an example to do the calculation for band theory. I'm not going to spend any more time in one dimension.
So let me, I don't know the answer for 2D. I've never.
And the 2D is also bound, it turns out.
So suppose let's say 3D.
Yeah.
I have this 3D periodic potential by the
right.
and one of the potential is changing to something much deeper, much bigger.
Right.
What will that create?
Well, that will create one bound state.
That will create a bound state, isn't
right.
it?
If it's
so if you make a semiconductor and if I put one electron, then it will be bound.
Yes, but the question is, if it had lots of such centers with weak potential, let's say, okay, then because the electrons like to, kinetic energy wants it to delocalize, we can make the assumption, all right, let's forget about the potential, let's just take the kinetic energy, and then we get a Fermi energy out, and if that energy is bigger than the binding energy, then you would expect that the metallic system is consistent. I'm not defending Mott's argument because I'm going to kill it in a few slides, but this was the first argument that was made. Okay? And it said that something is rotten in band theory. Okay? Something needs to be corrected. And he was pretty much alone at that time. I'll talk about an earlier calculation later on in this series. But
Ravin,
yeah.
so original idea gave a critical density for the.
Right, I'm coming to that. Yeah, I'm coming to that. So the point is that as the electron density decreases from being very, very large, where this almost free electron picture is right, with some kind of potential, the screening length increases and the hydrogen ion can bind an electron. Now, suppose you had an equal number of electrons and ions. Okay, let's take a phosphorus doped silicon with nothing else. Okay, so each phosphorus is an ion, and it can bind an electron in a hydrogen orbit. So starting with high density, the electrons are free and mobile as in a metal. And that is in fact experimentally seen. If you dope semiconductors very high, you find they are metallic. They're bad, not particularly good metals, but they are metallic. But as the density is reduced, the screening length increases, and at critical value of n, the ions can bind it. That was Mott's idea, basically. And then he said, well, if one ion binds one electron, you're still less electrons, so then the next one gets bound, and the third one gets bound, because then you're left with fewer and fewer electrons as these get bound, and it's a catastrophic transition. At some point, all of them will bind all at once. Even though we have only one electron per ion, we have an insulator, according to Mott. And that's in contradiction to band theory. Band theory would say, of course, band theory only would apply if the ions were completely periodic, but at that time, nobody worried about that. So, because the periodic potential was the only thing that could be solved in the 1940s.
So this argument does not require impurities to be there.
No,
It requires only electron-electron interaction with a perfectly periodic potential and everything.
No, it requires an electron ion interaction actually, if you think about it. That's what, because it's binding. That's so it's a little bit different from what we now today call electron-electron interaction. This is just basically saying that when you start out, let's imagine I put in a bunch of impurities. I put in the equal number of electrons, and these electrons, let's say, for some reason are in a free state. And then we're trying to figure out whether that's a stable configuration or not. And the answer is, if the ionic potential is very heavily screened because of the large density of electrons, that's it'll change a little bit, but nothing more than that. On the other hand, if the ionic concentration is very small and so is the electronic concentration, then the electrons would rather be bound to the ions. And that, according to Mott's original argument, was the metal-insulator transition. So it turns out that you can actually do this calculation. It's a one electron, one ion calculation with the screen Coulomb potential using Thomas Furby screening. And it turns out you can actually show, and this is not actually a very simple, I had to go into literature to find this exact number. Atomic physicists who have done that. It turns out that is exactly when A naught is the Bohr radius of the hydrogen atom, basically. Let me, okay. Which is h bar square over me squared. Okay, that's, I don't know whether I wrote it down somewhere or not. So if you take that literally, you would get a result that when the density is below this amount, given by NC to the 1/3 times the Bohr radius being about 0.36, these should bind and it should become insulating. Now, Mott was never somebody who was fond of doing exact calculations. He was an ideas person. And so he did it the best way he could. Okay. So another thing about Mott never got a PhD, even though both his parents were PhDs. He just felt that if you were a physicist, you really didn't have to have a degree to prove that you were one. And he had a very varied career from atomic physics into solid state physics and was a giant of British physics in his time. Anyway, what he did was he just said, well, let me just assume that the ground state is hydrogenic, e to the minus r over a star, where a star I'm going to treat as a variational parameter, and I'm going to calculate what that is. And for that, and using that variable radius to minimize the bound state energy, which is of course an upper bound, using that he got NC to the 1/3 times A naught is 0.25 instead of 0.3. As you can see, his numbers are not that great, but anyway, that was the number he gave in the 1940s. And since then, experimentalists have been actually looking at that. They've looked at a whole variety of systems from sort of ammonia and sort of sodium atoms in some sort of mixtures to doped semiconductors, normal doped semiconductors to a semiconductor like indium and Gemini, which have 500 times of Bohr radius, as you can see somewhere there. 500. Here is plotted the Bohr radius, and here is plotted the critical density, both on a log-log plot. This would say that you will get a straight line on this log-log plot, because it's 1/3 log NC plus log A naught is equal to a constant. And the slope is correct. And in fact, if you put it in, the best fit to this data gives that constant 0.26. So, it was declared victory. Basically, Mott was right. It was really a metal insulator transition for low density systems. The system was insulating, whether it had one electron or two electrons, it really didn't matter. And this equation, NC to the 1/3 times the Bohr radius equals a constant, is known as the Mott criterion. It still remains. It doesn't matter what the mechanism for the transition is, it's still called Mott criterion.
Ravin, can I ask a question?
Sure.
Do you have a feeling for why why? Because there's so many things left out in this theory. Why
Right.
this estimate works so well?
Well, it's sort of like 1 plus minus 2 plus minus 3 plus minus 4, etc., giving you 1 as the final answer. But you can get anything you like. I don't really know it. No matter what kind of theory you make, you know that this is the only dimensionless parameter in the
Yeah,
problem.
that I understand, but why should the number be 0.25? Not
It isn't.
not 1, something else.
In fact,
Or you can't tell in that. Suppose you had a different number there.
right.
Could you tell in this graph drawn in log scale?
Not really. Yes, you could change that number a fair bit because, as you can see, the data is scattered, and there is a little bit of difference between. The other question is, how well is A not known? Okay, and when you're talking about metal ammonia solutions, I don't know how good you can find the so-called Bohr radius, and so there's an uncertainty there. So I wouldn't put more credence to this formula than just the idea that it's okay on a log scale. It's whether I'm going to use it to 1% or 10% accuracy, I would be very skeptical. In fact, I'm going to show you some other people who took it very seriously and they got some results which didn't quite agree with data, and so we should. This is a historical portion, but it's important to get the history right, I think. Is that okay, HR?
Yeah, that's fine. That's fine.
All right. Okay. So let me talk about the successes of Mott at this stage. Okay. I apologize to all the people who know this story very well and know all the problems and things like that. But I think really this course of lectures is for the students to appreciate how physics progresses. I'm trying to give some sense of that. So in a sense, the point that he was trying to make was not that they were just binding, but then they couldn't hop from one site to another like in band theory, because the strong Coulomb-Coulomb electron-electron repulsion stopped the carriers from going from one site to the other. Because it costs a lot. If we come to this point in a moment, the hydrogen atom is bound by one Rydberg. Everyone knows that. If you talk about semiconductors, it's a Rydberg star, which is a renormalized Rydberg with a different, because the mass is different and dielectric constants and stuff like that coming. But then you ask yourself the question, what about 2 electrons on hydrogen atom? The second electron, it turns out, is very weakly bound. It's bound by 1/20th of a Rydberg. It's barely bound. Okay. So clearly, there's a large electron-electron repulsion taking place. Roughly 1 Rydberg of repulsion takes place, so that the second electron is barely bound 0. Okay. So, or 95% of the Rydberg is the so-called U for hydrogen atoms.
So in this last set of arguments,
Right.
where was the half filling there?
Okay, the half filling was there because if you don't have half filling, then there are some, let's say there are less electrons than there are ions, then there are some ions that don't have a bound electron, so you can hop an electron from one ion to the other because they are basically resonant with each other.
Yeah, but that is not, so in the formula that does not really take into
account compensated material. No, this is all for uncompensated material. Exactly 1 electron per site. There, we are talking about very, very old. At that time, people who were doing semiconductor physics didn't even sort of know what kind of semiconductors they had, and that's probably why actually Anderson's disorder idea caught on. In fact, Mott was the first one to catch on. He knew the problems with his model better than anybody else. Nobody else paid any attention. So Mott's analysis also shows that the interaction effects dominate at low densities. So we expect Mott insulator as opposed to band insulators in systems where the ions are far apart compared to the electron gate functions. So basically low density systems actually. And there are a huge class of compounds that are actually found in nature, transition metal oxides and chalcogenides like P2O3, nickel oxide, nickel sulfide, the high temperature parent compound, high TC superconductor parent compound, where the insulating behavior cannot be explained using that. So Mott's idea has significant merits. Now, I'm not going to spend a lot of time on Mott's ideas because it turns out that when one is looking at actual dope semiconductors and other disordered metallic systems, disorder effects are quite important, and that's not really part of Mott's story. So, but I'll at least tell you what the update is to Mott's idea. They've been put on a much sounder footing by incorporating electron-electron repulsion within a tight binding model. Because you might say that, well, all right, they're bound on these impurities, but then, I can make a tight binding model of these impurities, even though they're randomly placed, then I might get a half-filled band and I will get a metal. Okay. So that's one thing that's missing from Mott's original argument. One of the other, so this was what's known as the Hubbard model, which is used very much today. It was actually invented by a lot of people at the same time. Among them were Gutzwiller and Anderson also. Gutzwiller actually had a paper that it predates Hubbard's paper with the same model. But they were all simultaneous and in different parts of the world, so one name's stuck. So it's known as Hubbard model. But the most important thing is that Mott insulators can't simply, it turns out that these Mott insulators, because the electron still has a spin degree of freedom, they very often end up having some kind of magnetic order. So if I thought about this a simple cubic lattice of hydrogen atoms, one would naively expect that one side would have spin up, the next side would have spin down, then up and down, because antiferromagnetism is preferred. We'll get into that later on. But then, of course, the band theorists would tell you, all right, if that's the case, there's a spin polarized band, your two bands split apart, and therefore you have an insulator in band theory. The answer is that's not true. The splitting of the band, if you want to call it that, is way too small to explain. Okay. So it's not magnetism that is driving the metal insulator transition, it's rather the metal insulator transition that's driving the magnetism. And that's been substantiated by very good calculations that go well beyond simple one electron theory. More rigorous approaches were done by Volhard in the late 80s, and then in the 90s, the dynamical mean field theory was concocted to actually do much better than Mott's original argument. And basically what you find is that there is, as a function of the size of the lattice, you do have a weakly first order transition from the metallic phase to the insulating phase. So there is for tight lattices, you get a metal. As you go to looser lattices, you get an insulating phase, and there's actually a first order phase transition at zero temperature. And that zero temperature transition has, if you will, if I write temperature density plane, there's some kind of a line here terminating in a critical point above which you can continuously go from metal to insulation. And that's quite independent of magnetic ordering. These kind of theories, you can suppress them on magnetic ordering artificially and still get a metal insulated transition. There is a magnetic transition out here, but that happens around there, not at the critical point.
One question.
Yes.
Why does this line terminate at a finite temperature?
just like a solid liquid, same physics. It's just an electron liquid going into an electron solid. Yeah, it's a very similar. The physics is slightly different, more complicated. There's a lot of quantum mechanics there. You don't need quantum mechanics to understand solid liquid transitions. But essentially saying that is the general piece.
It's always first order.
Yeah, it's always first order up to a point. And after that, it's just a continuous. This is for the lattice case. This is not for the disordered case. Okay. So in fact, you might think that if you now add disorder, this first order line will go to 0, and then there'll be a continuous phase transition at 0 temperature. So Mott's explanation was actually motivated, as I said, because of doped semiconductor. If you put an impurity, also called dopant, it forms a shallow hydrogenic atom, for example, phosphorus in silicon or arsenic in germanium, because this is just group 5 element going into a group 4 host. And because of the hydrogenic nature of the impurity wave function, so for the aficionados, I'll be talking about only N-doped semiconductor, because that's much easier to deal with. The valence band has spin-orbit coupling and all kinds of other complications that are not essential to this problem. So all the experiments and all the theory that has been done with N-type doping, extra electrons. So they go into the conduction band of the semiconductor. And doped semiconductors are actually found to undergo metal insulation. You start from an insulating phase, you increase the doping, you keep on increasing it, and it becomes a metal. That every single doped semiconductor does that. There are some that have other structural issues, but that's only at very high doping. So let me then at least introduce the dopant problem to everybody, so everyone is on the same page. Those who have never seen it can get to where all the others are. So the idea is that you start with a semiconductor host. So that's and the Hamiltonian of that system is the crystal Hamiltonian. It's a crystalline system, so it has some crystalline Hamiltonian. And then you imagine you put one of the atoms here is phosphorus instead of silicon. And if you look at phosphorus, it is equal to silicon plus 1 nuclear charge plus 1 electron. There may be some neutrons also in there, but they're benign, not important to our problem. So this die is a phosphorus plus. Because there are one extra nuclear charge and one less electron compared to silicon. Now this phosphorus plus acts like a silicon atom, exactly the same bonding structure. Everything is the same. And so that looks like a silicon. But then there's one electron, and this one has a Coulomb potential, which is this one right here. That's the interaction between that extra electron and the nucleus. And so that's what you need to solve. Now you can take the point of view that the dielectric constant of your semiconductor is pretty large. Most semiconductors have dielectric constant 10 to 20. Okay, so that's a pretty large number. So one assumes that this is a small potential, and you can do perturbation theory, what's called the effective mass approximation, and you can write down the wave function of this extra electron. Normally, this is the band structure of silicon or any semiconductor. There's a valence band, plotted T versus K. Here's the valence band, and there's the conduction band. Now, for aficionados, of course, conduction band is not minimum at K equal to 0, but let's not worry about that right now. So if you had a single electron and no potential, then that electron would sit at the bottom of the conduction. You would say that its wave function is going to be equal to K equal to 0, or the wave function at the bottom of the conduction band, which can be at finite. So I allowed that 5 K naught to power in the clock wave at the bottom. But in fact, because of this potential, it turns out that this is modulated by a hydrogenic envelope, and this hydrogenic envelope precisely follows this the hydrogen equation. It's exact. The only thing that is different is that this is m star, the mass of the conduction band coming here, and this is the dielectric constant that is only there because the potential is down by the dielectric constant. So when you do that, now there are complications. Your mass may be anisotropic, so that it may not be exactly hydrogenic. It may be an anisotropic hydrogen atom problem, but those are technical details. What you will get is you'll get the 1s, 2s, 2p, etc. states. Right? Because of mass anisotropy, the 2s, the s and p states don't have to be at the same energy. They might be slightly split, things like that. But you get this infinite. And then finally, you have a continuum, which is just the conduction band in this case. So you sort of, this is a flow up of that picture here, where I've said that's the ground state of the impurity, but there are excited states also possible. And you can estimate what the Rydberg is by putting in the mass of the conduction band and the dielectric constant, and you can estimate the pore radius again the same way. And it turns out that in germanium, this Rydberg is about 10 millivolts. In silicon, it's about 30 millivolts. In the Bohr radius, it's 50 angstroms in germanium, 20 angstroms in silicon. In gallium arsenide, it's 100 angstroms. And as I said, in indium antimonide, it's 500 angstroms. So the main message is it's much, much bigger than the nearest neighbor distance in silicon or germanium or gallium arsenide. So on this scale, the hydrogen atom is just a continuum. The lattice is just like a continuum. Because you're talking about a wave function that's fat and big, and the lattice structure is very, very tiny, on very tiny scale. So we don't really need to worry about that, other than the fact that there is the block wave that's coming here. But the physics of this system is very similar to that of hydrogen atoms in free space.
So the fact that its scales are very different is mainly due to epsilon being not a 10 or 20 or...
Yeah, it's basically m star over epsilon is 1 over 50 roughly. No, that's nature. It's another reason why, Krishnamurti asked the question, why is NC the 1/3 times A equal to a quarter approximately? If you write it as NC AB cubed, A naught cubed, then it's 1 over 64, which is a small number. It's almost halfway to the fine structure constant. So it turns out that because that number is small, and I have some reasons to believe why nature wants to be metallic, and it tries to become a metal as soon as it can. And so that's why that number is small, I think, in reality. And because it's small, a lot of theories that start from the insulating phase actually do very well. If you start from the very nice metal, very fully screened, try to come to the metal insulator transition, you do much less well. So if you're interested in the metal insulator transition, starting from the insulating side is somewhat easier, I think. That's my regular situation. So now I'm going to make that this so-called calculation of where the electron energies lie a little more quantitative, not as much as dynamical mean field theory or anything like that, but this is sort of Hubbard physics at the lowest level. Okay? So the idea is the following. I'm going to imagine this is the density of carrier, and I'm going to put the last electrons on a cubic lattice. No, I don't have that picture. Somehow or the other, I've had a cubic lattice somewhere in the middle in one of the slides, but it's not there in this one. Okay. So the electron that's bound to the ion is at -1 Rydberg in this unit. The second electron, which isn't there right now, is only bound by 0.055 Rydberg. This is very well known. This is an exact, in fact, 5545 is known to 4 digits. And one case where the theorists can do better than the experimentalists. Because it's just a 2-electron problem. Okay. So you can do a 180 variational parameter calculation and get 5-digit accuracy without any difficulty. So it's there. Now, as you increase the density, these bands will will broaden because there's hopping. But the important thing is that these two bands are split. This is two split bands starting from zero density. Unlike in band theory, where up electron and down electron have the same energies. Now, you can't quite call it up electron and down electron. This is singly occupied, that's doubly occupied. But you can sort of take you can say, all right, I'll close my eyes and I'll just say that the down spins have lower energy and the up spins have higher energy. They're trying to make a connection with one electron physics. So I'll imagine this is sort of the down spin electrons, and those are the up spin electrons. Okay. And if I take that, actually what I've basically done is done a band structure calculation for a ferromagnetic arrangement of these ions. And when you do that, you find that here is this band. This is an actual calculation that Maurice Rice and I did, 1980 or so. Then it was rechecked by my grad student who did a much more detailed calculation. But what you find is this band grows very, very slowly. On the other hand, the upper band, because the wave function is very fat, its hopping is very, very large. And so it really broadens very quickly. Already when the distance in the cubic lattice between nearest neighbor is 10 Bohr radii, it's already come down quite a bit. So anyway, this MV and SV corresponds to multi-valley and single valley. I won't go into those details. But no matter which one you take, you find that you get a metal insulator transition roughly when the distance between the cubic lattice distance to the Bohr radius is around 4, which is this inverse of 0.25. So
this is a variational wave function calculation.
No, this is actually what I do with the following. Here I take a tight binding because I think the 1s wave function is very very tightly bound.
Yeah.
Here, what I do is there's actually a calculation that is done. It uses polarization potentials. You imagine you have a neutral hydrogen atom, and you take an extra electron with very low energy and consider scattering of those. Now it turns out, interestingly, Mott had actually done that calculation decades ago. But when he got John Davies to do this same plot, he forgot about it. We saw it, and there was a paper by Temkin and Lampkin in atomic physics that did that in great details. You get a pseudo potential for the second electron, basically, and you then calculate within that pseudo potential. So that's what this calculation is. The main point is that no matter what you do, these bands suddenly broaden roughly at when R over A is about 4. And some will be slightly less, some will be slightly more, and people with different approximations will get different results. But I'm trying to suggest that it's basically this, and this one basically vertical at some point. Okay. Now, having talked about all the good things that Mott did, let me now come to the problems with Mott's idea. The first and most obvious problem is compensated semiconductors. So now you imagine that you have phosphorus and silicon, but then you also have a few boron, which will rob the phosphorus electrons, because boron is trivalent. It wants to become quadrivalent, and therefore it'll just take away the electrons from it. So what has happened? Number of phosphorus ions is larger than the number of effective electrons in this system, because the boron has robbed some away. Then we go back to this. What that says is some of these electrons are out, and the Fermi level is somewhere there. It's a metal. Doesn't matter where you are, what density you are. So Mott solved the problem exactly for half filling, but he couldn't solve it for any other filling. And in fact, semiconductors that are compensated and low density are just as insulating as uncompensated semiconductors. So, Mott realized that this was a huge problem with his model. And the reason is that the electrons because not all sites are occupied, you can have hopping from site to site, and then that's, I mean, we are, with 70 years of hindsight, know very well that there's disorder, and so hopping is inhibited by disorder, but we have not yet come to Anderson. So we are a decade before Anderson.
This is also why when Anderson came up with this paper, which was also not quite celebrated at that time, Mott was the one person who kept writing paper after paper saying this is something what you have to do.
Yep. No, I have that very slight. No, it's okay. That tells me that people are engaged. Okay. Now I'll give you some more detailed problems. Okay. It turns out that many semiconductors have degenerate conduction band minima. For example, silicon has 6, germanium has 4, aluminum arsenide has 3, whereas others have single conduction band minimum like gallium arsenide. So you can repeat the Mott's argument where you put the electrons instead of a single conduction band minimum, you sort of equally partition them among all the different conduction band minima, and it doesn't take much thought to realize that the Mott criterion will change because the number of conduction band minima will be important. The screening length depends on the density within each conduction band minimum. Okay. So this was actually done by Green, Aldrich, and Bajaj somewhere in the mid-70s, just about the time when I got into this business. And Chuck Aldrich was a student of David Pine's, and so I knew him at Illinois when I was a grad student. And they did Thomas Fermi screening using hydrogen trial function, just like Mott did. Then they used a Knudsen trial function, which works much better. There's your 0.36, it's giving it pretty well. Okay, this again is a trial function, it's not an exact calculation, but nevertheless, the numbers are much closer to exact. And what you see is that it doesn't matter which function you use, depending on whether it's a single valley conduction band or 4 valley conduction band, 6 valley conduction band, you get very different Mott criteria. This is this number 0.25 that Mott called MC to the 1/3 times flow radius. And here it's 0.1, it's 0.28. And this would make a huge difference on that plot. And you don't see that. If you actually look at the data within doped semiconductors, it doesn't seem to agree with that. Such a dramatic difference. I mean, you can 0.25 could become 0.3, it could become 0.21 or things like that. But 0.08 for silicon, no way. So that brings me to Anderson. And it's a completely different approach. It's not an approach that depends on what electrons do with each other, but it has to do with the fact that the system is actually not a lattice system. When you have impurities in semiconductor, they go in randomly. But they go in at high temperature where there is no real potential entropy is the biggest factor, and therefore they basically land on random positions in the silicon lattice. And just to get the numbers right, because the Bohr radius is so large, we are always talking about dopant densities that are sort of 10 to the 17, 10 to the 18, 10 to the 19, which is several orders of magnitude less than the atomic density of the semiconductor. So it's, the dilution is incredibly, it's a very dilute system from that point of view. The number of dopants to the number of semiconductor atoms is very small. Okay. So Anderson, what he did was he basically said, all right, I'm not going to worry about the random positions, but I'm going to put in some kind of randomness in the problem because, and this was in some sense the beginning of Mott in solid state physics. Until then, people tried to do as good a job as they could. And Anderson said, I'm not going to worry about that. This is ubiquitous among all these systems, so there must be some commonality, and I can just probably do the best model I can. Now, the actual calculation experiments Phil was trying to explain was really spin diffusion. And in those semiconductors, but he didn't know how to solve the spin problem. So he solved the single electron problem instead and came up with this amazing result. So what did he do? He basically imagined that you have this cubic lattice in 3 dimensions. Okay? These are your dopants. They are placed on a cubic lattice. Rather than making their positions random, what he did was he said that let's just assume that each of them has a different energy. So he put epsilon I as the on-site energy, and this is in standard quantum mechanics notation, that's in second quantized form. And then there's some hopping between a site and its nearest neighbor. That's where my cubic lattice disappeared. I should have put it in the other slide as well. So that was the case for which we did the actual band structure. And he took very simple assumptions for the this probability distribution of epsilon I. He said each and every one is independently chosen, and it is chosen from this distribution, uniform distribution with a cutoff. So there are 2 energies in the problem. One is what we call the disorder energy, which is the width of this, which is W, and the other is the hopping T. So in fact, the only thing that matters is the ratio of W over T. One sets the energy scale overall, and the other one sets the how much disorder there is. So since T only sets the overall scale, we just set T equal to 1 and just measure W units of T, and that's the solution of the problem. Of course, 20 years later, this particular paper got the Nobel Prize. But at the time when it came, nobody in the United States really recognized its significance. Maybe some people at Bell, some experimentalists were persuaded, but none of the theorists liked it. In fact, most theorists tried to disprove it. And it turned out that they managed, there was a guy called Lloyd who had a Lloyd model which had no localization whatsoever. And part of the problem was that his model was such that one can use average green function, and that's not really what one should do. So he has a little bit of caution to people who are very mathematically inclined. You first need to know the physics and then figure out what you need to calculate. Don't just calculate Green's functions because that's the easiest thing to do. Okay. If you had done that, you would have got the wrong answer to the answer, at least at that time. Okay. Okay. So this is Phil Anderson, who just passed away a couple of years ago. I had the great honor of being his colleague from 1976 till he died. Basically, he would power at Bell Labs, and then he moved to Princeton half-time, and then he moved to Princeton full-time, and I moved to Princeton. So anyway, the point that he's trying to show is that diffusion is what gives you finite conductivity in metals, and his paper purported to show absence of diffusion in certain random lattices. Of course, they are random lattices in the sense that the on-site energy is random. That's where he could do the calculation. Okay. So how does this actually work? Okay. If W is 0, all the eigenstates are itinerant because then they just hop, nearest neighbor hopping model. Okay. And you have a density of state that looks like that. Those are the gamma, x, m, and r points. For those of you who are into band structure, that's the center of the Bernoulli zone. This is the x point, which is along the 1, 0, 0 directions. M is along the diagonal, and r is at the core. Okay. And what happens is the density of states, as you start increasing W, these things get rounded out, and you get localized states at the edges, and then eventually at some critical density, it turns out that all the states get localized. By localized, it means that every single state, none of them extend throughout the system. There is some center from which at large distances it is exponentially decaying. And if you look at the phase diagram, you can write it as W over T versus E over T. And it turns out for this model, actually, there is a band edge, well-defined band edge, because it has a sharp cutoff of which are these two lines. And then here is where the extended region is at center of the band, and then in the tails are localized states. And actually, this thing closes incredibly sharp. It's very flat. If you do numerics, that's how you find it.
Why this small bulging?
Why does it bulge? That's only for this uniform distribution. If you take Gaussian distribution, it's much smoother. Then it's more like. The bulging is because of resonant effects. If you have lots of sites at the edge of the band, they are resonant with each other, and so therefore they become extended. That's something that my student Sonika Jory did extensively in the past 15 years, and we found out that there are actually singularities in this model which everyone has been shoving under the rug. But that's all because of the fact that this is a sharp edge, which is, a model after all.
So do you get the localization if you disorder knopping amplitudes rather than segmentation?
Sure, you get that too. In fact, when I come to the magnetic problem, I'll show that we have to do that. We're going to try and explain experiment. This one will only work when it comes to very close to the mobility, what's called the mobility edge. This is called the mobility edge. There is a particular energy which separates the localized states from the extended states. This is a one electron problem, so you can do lots of numerics with it. And in the vicinity of the mobility edge, the behavior of the Anderson model is the same as any non-interactive. But elsewhere, it's of course dependent on the particular model you have.
So it's sharp coming in
Yeah.
the WX. That's also because of the sharp cutoff, like Gaussian.
Yeah.
Gaussian would also smooth these.
Yeah, Gaussian is much more smooth. So yes, the sharp. So a lot of people have sort of, but it has an advantage. Okay, for example, Shklovsky and company use the fact that this is so flat to analyze all these states here to try and understand distributions, like whether it's Wigner Dyson distribution or Poisson distribution of eigenstates and things like that, because they are all very close. Yeah. So you basically at this energy, all of these are extended and all of these are localized. So whereas if it was much more rounded, then you would have to be careful, right? Much more careful. So this is I don't think Phil was aware of any of that, and he probably didn't care about that.
So, in this localization, the rough criteria that one uses
Yeah.
is KFL to be of the order of 1.
Yes, I'll come to that later. I'll come to that in the next lecture, not in this lecture. Okay. And in those days, people didn't talk about KFNL, they talked about T over W. That's all that was important.
T over W is not an experimental parameter.
No, it's not. No. I'll get to experiment. Here we have sort of taken a step back from experiment, if you will, because Anderson's model is so stylized. It's not the real truth. Okay, but he must have had some inkling that near the transition it mattered, and he was actually just trying to establish that there was a localized phase, which nobody believed before, because the assumption was that Bloch's theorem says everything is extended. Right. So how did Anderson actually do the calculation? So Anderson has said repeatedly, it's a paper that's oft-quoted and never read, because it's so hard to read for most people. Okay. So I will give you my interpretation of Anderson's paper. It's a very pedestrian interpretation, and I hope that at least that much you can get, and then maybe you can read it in more detail and get the end. So in the zero hopping limit, that is, where T is equal to 0 but W is finite, then eigenstates are localized on individual sites. right? Because imagine, sorry, where am I? One more slide back. If T was 0, then I already have a diagonal. You know, those are the eigenstates. Their eigenenergy is epsilon I and the eigenvectors are I. Each lattice site has an eigenvector. So they are each localized. And then what he did was what's known as a locator expansion. Locator expansion is basically trying to do a perturbation theory in T over W. Treating T as a parameter. So he wants to start from the localized side and then show that for finite T over W, it remains localized and does not become extended all of a sudden. So he basically shows that for small T over W, this perturbation theory converges. That's the way he shows it. Right? So the eigenstate that he surmises as the result that the eigenstates are localized exponentially from each other. Why? Because every time it needs to hop to another site, you get a factor T over W. So if you want to go to n sites away, it's T over W to n. And that's exactly how exponential function behaves. It's every fixed distance, you have a multiplicative factor, and that in this case is T over W. And if T over W is small, then that multiplicative factor is going to be smaller and smaller and smaller, and that's an exponential function, decaying function. Now, there are many subtle points here which are not realized by most people. The first thing is degeneracies. What happens if you have two sites that have the same energy? Then when you take the perturbation theory, okay, you're going to do T over epsilon I minus epsilon j, and if epsilon I equals epsilon j, there's no perturbation allowed. But the solution to that is, instead of using the standard Rayleigh-Schrödinger perturbation theory, you use the Grimoire-Wigner perturbation theory, where you use the actually renormalized energies, and then you get rid of the problem of degeneracies. Second point was not understood by a lot more people. The only one person that I know who understood it very early on was David Hubbard, which is that, what does it mean for
Ravin, if I may ask a technical question, this switch from Rayleigh-Schrödinger to Brillouin-Wigner,
yes.
At least the way I remember learning Brillouin-Wigner is that you basically get a self-consistent equation for a set of energies. You don't get an answer for the spectrum.
No.
So it's some sort of resummation of the Rayleigh-Schrödinger. So
exactly.
What do you do to that self-consistent equation to get rid of this degeneracy problem?
No, the point is that when you do the self-consistency argument, what you find is that when in the end, the point is that eigenstates will repel each other, right? So there'll never be a problem. But people gave this kind of grief to Anderson, saying that your on-site energies will turn out to be the same, and your series will blow up. So he had to at least assuage the people who were asking him these kinds of questions. That in fact, no, it doesn't blow up. I mean, it's all well defined, even though you think there are cases where it might, where eigenenergies might be very close to each other. Typically, in an insulating phase, eigenstates that are very close in energy, we now know, are very far apart in space. So they are connected by very high order perturbation theory.
Right.
Yeah, we know that now, but at that time, people didn't know that. They sort of thought, there may be eigenstates that are very close to each other in space and in energy. They were not quite aware of.
And then the statement is that the renormalized energies you get by solving the Brillouin-Wigner self-consistent equations will cure this problem.
It will cure the problem, right?
I see.
Yeah. So the more subtle point, I think, this one is something that most students will also recognize, that there are many problems where you don't want to use Rayleigh-Schrödinger perturbation theory, at least to second order, that you find that you get degeneracies and problems. And Brillouin-Wigner solved that. Basically, Dyson's equation, self-consistent. But the other question is, what does it mean for a series to converge when the energy denominators are random? What do you mean by that? How can you talk about a series? There will always be some cases where the series may not converge very well. And the answer there is that you have to use ideas from probability theory, that the actual statement is that the series converges with probability 1. Not that every single sample will be. I can make a sample where the Anderson localization won't work very well, but the probability of having that kind of a configuration is exponentially small in the number of sites or something. So it doesn't contribute. You have to deal with typical sites. And this business of typical versus average is another thing that got a lot of people into problems, because everyone knew how to take means. Nobody knew how to think about distributions and typical values when the distributions are not Gaussian. And finally, I just want to mention that Anderson was actually trying to understand spin localization, but he simplified the problem because he didn't know how to do that.
One question.
Yes.
Wasn't there also some uncertainty about when you expand, there are these loops where you kind of come back to the same point.
Right.
Somehow you have to show that they are not going to screw up your.
Well, there was something that in weak localization, those are very important, right? But Anderson was not interested in that. He was interested in the situation far in the insulator, show that the insulator existed for a finite range of parameters. That's what he was interested in. So Mott realized, very few people realized the significance of Anderson's paper. Okay? Mott was the one who did, because he immediately recognized that this is why compensated semiconductors remain insulated, because it's disordered. It can't be just electron physics. And then he, with tools, showed that for a one-dimensional model of Anderson model, all states are localized for any disorder. I mean, you can have very weak disorder, the localization length will be large, but it will be finite. So he showed that in one dimension, all states are localized. And he also showed that localized and extended states cannot coexist. And that's how he defined the concept of a mobility edge, which is the energy that separates the localized states from the extended states. If you notice in my figure here, these are vertical lines. They're not changing in energy, okay? Which is saying that either the state at that energy is localized or it's extended. You can't have both of them. And sort of a hand-waving proof is that suppose you had you had a localized state alpha and an extended state beta having the same energy for some configuration of EIs. Okay. Now you put a little change in the EIs. You look at the Hamiltonian, the 2x2 Hamiltonian for those two states. And you'll find that both the diagonal terms and the off-diagonal terms are going to be proportional to that change you made. And so they will mix. Okay. In fact, if I just take the off-diagonal term, don't add anything to the diagonal, I know that in fact the two eigenstates are alpha plus and minus beta. So they've completely changed because of this order, which means that if you have a given sample where a localized and an extended state exists for slightly different parameters, they will not be at the same edge. They'll both become extended, basically, because any linear combination like that will always be extended. Let me see how many. I don't want to. All right. We'll continue.
Ravin, one more minor question about this no localized states in the middle of an extended continuum. The argument you just gave, saying that if you make any linear combination of two things at the same energy, it's a valid state and it will always inherit the extended character of the extended part of that linear combination. That was the argument, right?
It's the argument, yes. Absolutely.
Yeah. So, but then that's kind of almost tautological, right? The question one might want to ask is, can you construct at least one maximally localized orthogonal basis where some of the wave functions are localized, right? That's a different question. Have people done anything about that?
Can you say that
So what
again?
I mean to say, is there some orthonormal basis of functions at that energy such that some parts of that basis, some basis vectors are localized and some are extended? It's not even clear to me that any one basis like this exists, which is a stronger statement.
Yeah,
So have
I
people
don't
thought
know
about
the
this?
answer to that. I don't know the answer to that, but that's certainly an interesting question as to how many. I mean, I know the answer in the case of the quantum Hall problem, that there are topological and non-topological states
Right. So that's what I had in mind.
Yeah.
Exactly.
There it does seem to be. That's what numerically comes out. I still don't know whether anybody knows why it is so. I mean, I have yet to ask and get an answer to that. I'll get to that in the last two lectures, or the second last. Sure.
Thank you.
Okay. So Mott actually also began thinking about the electron transport in the insulating phase. Once he accepted the existence of the insulating phase, and he discovered what's known as Mott's variable range hopping law, which governs the ZC conductivity at low temperatures. And it turns out that it has a very strange form. It's not like in a normal insulator where you have a prefactor and an exponential minus some gap divided by temperature. It's, in fact, in 3 dimensions goes as some temperature T naught over T equal to 1 over 4. In 2 dimensions, it would be 1/3. In 1 dimension, it would be 1/2. This is Mott's law. And we will, in the next, I don't want to extend today's lecture. I'll start from where I finished and go on to the second lecture. When I'm done with the first lecture, we'll stop with this particular slide. And it turns out that this is a much larger conductivity than in a uniform insulator. In a uniform insulator, this form dies very, very fast, you see, exponentially. This dies as exponential of 1 over T to a fractional power. So it's exponentially larger than that. So one of the predictions of this kind of approach was that disordered insulators are much worse insulators than regular band clean insulators. And since almost everything has some amount of disorder in it, it also tells you that there is a conductive path through the disordered system, which is more optimal than exciting an electron to the next band and having it propagate like a diffusion. So, in fact, because you can do optimal hops. There are various different points where the electron can hop from one impurity to another. So here the positional randomness of the impurities is very important in Mott's argument. And we'll go through that, Mott's argument for that, and then a little bit later, I hope I'll have enough time to cover the more rigorous treatment of Ambedkar, Halperin, and Langer, which is I think one of the most beautiful papers written in condensed matter of that in the 70s before I started. So I think I'll stop at this point because we have only 2 or 3 minutes left. And if there are further questions, either from the room or from people in on Zoom, I'm open to that. Yes.
What is the scale not determined?
I'll come to that. It depends on density of states and distance between average sites and things like that. It was one of the amazing results that Mott managed to get, and I will present Mott's argument for it. Okay? It's a typical Mott calculation, back of the envelope, and there it is. And a lot of people wanted to disprove it, In fact, Ambegankar and Langer thought they had disproved it. They got Halperin as a referee who corrected their paper, and eventually it came as this is what I've heard. I don't know how true the story is, but this is the folklore in the community. I mean, I was a graduate student in those days, so didn't know anything better. Maybe, yeah.
What sense do you mean optical over here? To go back to a few slides when you were talking about, okay, that Anderson model, you have to think about convergence probably.
Yeah, but this is not for the Anderson model. This is actually for randomly placed sites.
Sure, but you still have the same premise of random disorder here.
Right, and then the question is, obviously, if your wave function has to tunnel from here to this side, it goes exponentially with the distance. But then there's an energy denominator in the problem too, and the energy denominator decreases as the distance goes up. And so you have to optimize between those two, depending on what the temperature is. Because one is temperature independent, the other one is temperature dependent, and so then you end up with an optimization problem, which I'll go through.
No, but this is not a statement about convergence probability.
No. It is very simple. This is Mott never believed in very high mathematics. He sort of
said that was the question.
Yeah,
whether it's a probability statement or whether it's just
no. It is a statement what should happen. But many people thought there was a problem with this simple-minded argument. So it actually was rigorously proved by Bhatt was in those days a young physicist who did his thesis on one-dimensional localization and didn't even mention Anderson in his thesis. That's an interesting fact I found out later. But he was interested.
This was Bhatt's thesis.
Bhatt's thesis. It was done under John Hopfield, who was his advisor. But I think Bhatt did it himself, basically. It was very mathematical, typical Bhatt. Any questions from the audience on Zoom? Or have I put everyone to sleep?
No, not at all.
Okay, all right.
One last question.
Sure.
So this variable range hopping, because we've seen in experiments, but like 1 over d plus 1, how solid is it?
It's not solid. In fact, I will give you all the data.
Okay.
I mean, this is one case where electron-electron interactions do matter. It's something that was pointed out by Afros and Shklovsky. And as far as I know, that result holds still today. So I will go through that in the next section. I mean, I won't go through Afros and Shklovsky. That will come after I talk about interactions. But it's important to realize that disorder and interactions are both important in this problem. And sometimes it's better to concentrate on one or the other. Sometimes you have to mix the two. Then you have to end up making some approximation of the other. All right.
Is there some general wisdom in the community about kind of quantities that interactions must be taken example of? Is it just case by case that you look at this, it does what, now have to put it in?
I mean, in the insulator, there is no reason to think that interactions don't matter, because you're really talking about localized wave functions, and so you're starting with the basis of localized functions, and that's not very different from point particles. So if we had only classical electrons, they would big enough crystallize at any density, right? They would. Yeah. Okay, in that case, we'll meet again on Wednesday at 2:30, and I'll continue from there.
Thank you, Ravin.